The title of Shucheng's talk is Cross-Layer Cybersecurity Research from Wireless PHY Layer to Machine Learning and Distributed Trust. Shucheng, you're on.
Okay, can you see my screen?
Yes, we see you.
Okay, hold on.
Yeah, you need to share your screen.
Okay, can you see?
Yep, excellent.
All right. Okay.
Hello.
Yeah.
Okay. Okay. Good afternoon, everyone. I hope you enjoyed the talks, the great talks so far. My talk is the last one. The title is a cross-layer cybersecurity research from a wireless physical layer to machine learning and distributed trust. Basically, my research is from, of course, this is my recent research interest is from the observation to different security issues in the smart systems. So I drew a simple diagram of most smart systems. You can see that most of these systems are cloud-based, and they are driven by some small devices, what we call IoT devices. And on one hand, so we have like millions or even billions of IoT devices around the world, which make complex smart systems. And also these systems will generate a huge amount of data, and they usually store the data in the cloud, and which facilitate the massive data analysis and also machine learning, AI. But a lot of security issues exist in these complex systems. If you look at the bottom of the system architectures, you can see that many in the real systems, many securities originated from the vulnerabilities of these small devices, and they are poorly protected. They have a huge amount in population, and they have very limited resources. Most of the time, they are heterogeneous, and also you usually like frequently install and uninstall them, and they have different lifetime, and they have different programming interfaces, and of course, they are used by different kind of users. So therefore, it's very easy to introduce some security problems, and also some traditional security solutions, such as cryptographic solutions, may not always be applicable because some devices are so small, they don't have the computational power to support expensive cryptographic primitives. And also there are also some usability issue, and also scalability issue, okay, with traditional security solutions. So on our side, okay, the massive information collection and analysis also introduce a lot of problems, which include data privacy issue, and also which of course include the model privacy, and also we also worry about some adversarial inputs to the system, okay, to disrupt the system. And what makes the problem more complex is the large scale distributed fashion of the system. So today, okay, I'm going to address my research on these aspects. So first, okay, for IoT security, so my research is mainly focusing on the wireless physical layer. So which means that we want to investigate the physical characteristics of the IoT devices, from where we want to bootstrap the security and the trust. For example, the question is, can we identify the wireless device by just looking at the wireless signals we received? Actually, if we look carefully, so we can see that every pair of wireless devices, they share a unique and a random channel. So this provides opportunity for us to identify the devices and also extract the secrets from these channel characteristics. But of course, there are also other characteristics people used for identification and the security bootstrapping, which includes the audio information, the motion information, and also other physical properties. And in our research, we particularly focus on the wireless channel, because for any IoT devices, if they want to communicate, they need to share the common communication channel. So usually, if we look at the commodity devices, these like these Wi-Fi devices, Bluetooth devices, they are very popular. So no matter what manufacturers they are from, so they share the same communication radio. So therefore, we can find something in common for these heterogeneous devices. From these common resources, we are able to bootstrap security. So actually, if we investigate carefully, we can see that even we compare two devices from the same manufacturer, they are not perfectly identical. So there are some like imperfect hardware hardware issues. They also have some transceiver signatures due to the different part of the hardware component. So therefore, we want to. It seems like there's no identical leaves in the world. So we use this philosophy to bootstrap the wireless security. So actually, there are many sources for wireless physical signatures to extract, but not all of them are applicable for identification and security bootstrapping, because on one hand you need this signal or signature to be kind of stable and unique, and at the same time it should be random and also not change due to the surrounding environment. So we can identify several components. This picture demonstrated the typical wireless system. You have in a typical MIMO system, so you need to first modulate the signal, then you go through a lot of signal processing, and also at the receiver side, the different hardware components will process the information, and at each part of the system, so it will introduce all kinds of errors. In the communication setting, so these errors are usually not good, so they disrupt the quality of communication. But for security, we can utilize them as a unique signature for bootstrapping the trust. So in our research, we of course we need to consider both security and the implementation issues, because we do not want to stay in the theoretical research. We want to make it happen to real devices. Therefore, these signatures should be extracted through implementation. So in our work, one example is we use the so-called CPO. This is the phase offset caused by the initial phase locker. This is a time invariant error. But at the receiver side, this error is combined with all kinds of other errors. So then the problem is, how can we extract this error precisely to identify as a signature to identify the transmitter? So there's a lot of signal processing and also data analysis algorithms we designed. We did some experiments on real devices. So first, we did on the control setting with a wide connection between the two devices, and we see kind of a perfect pattern that can help us differentiate the different wireless devices. And then we move on to real world devices. Okay, we did experiments in different settings, indoor settings. Okay, we use the cards from the same manufacturer, and we are able to differentiate them. Okay, even if they are just a very slight difference. So this line of research is just an example of what we did to bootstrap security from wireless physical signatures. But of course, there are big space for to explore. So we can also use all kinds of other physical signatures. One nice thing of physical layer security is that we do not rely on cryptography. We do not rely on any central authority to distribute the secret key. And the only thing you need to do is to remember. Okay, first of all, maybe we need to train the system a little bit. Okay, then you know the signature of the other device. Later on, so we can measure the signatures on the fly, okay, in the real time, okay, in a very, very fast fashion. Okay, I think this is a very good technique as compared to traditional cryptography. Okay, in the large scale IoT setting. So the other direction of my current research is also on the machine learning. For example, okay, we are investigating the security issue of federated learning, which has been introduced by the previous panelist. So in particular, okay, we found out this federated learning, okay, they has some advantages and disadvantages. Of course, we have understood the advantages. It does, with federated learning, these clients do not need to transmit the data back and forth, and they just train the model locally, and they just submit the local model to the aggregator. And therefore, okay, we can preserve the data privacy. But the one big problem is that, okay, since the clients need to submit a local model to the aggregator, so from this local model, so some attackers can still infer some information. So this is called the model inference attack. So for example, they can kind of infer what kind of training data it uses. Okay, therefore to breach the data privacy. So to address this problem, okay, the community has used some techniques. For example, differential privacy. This is one technique, but for differential privacy, okay, there's a kind of privacy versus utility problem. So another solution is encryption. So this is a very traditional solution. So imagine, okay, if we encrypt the local models, then okay, the aggregator, assume the aggregator is able to do the aggregation with the encrypted model, then the attacker will not be able to get anything about the local model, okay, unless they can break the encryption key. This solution sounds very good, and it's also proposed by Google 3 years ago. But the problem is this technique also introduced another issue, which we call the model poisoning attack. So because every client encrypts the local model, nobody except himself knows the local model. So we don't know, okay, whether or not the model submitted by clients are legitimate or some malicious model. For example, okay, if some malicious clients want to mislead the global model, okay, they can submit very large parameters, okay, which will kind of dominate the global model during the aggregation process. Since the local models are encrypted, nobody can find out. So this is a severe problem, and we did some experiments, okay, on this kind of solution. Even using one attacker, so we are able to completely disrupt the global model. Okay. So this is a very severe attack. And we introduced some technique to address this problem. Basically, okay, we introduced some randomness in the setting. We group the clients into some subgroups, and then we randomize their position. Okay, then we within each subgroup, we do some masking, and then we review the partial information of the subgroup model, okay, to the server, but we encrypt the most part of the model. And with this, okay, we can allow for the anomaly detection. There are a lot of research going on in the machine learning community, which focus on the anomaly detection. So if some users submit the malicious model, so they can detect it, but they are working on this problem in the unencrypted model. Okay, but our work is we want to allow the same technique over the encrypted models. And we also prove that this kind of disclosure will not reveal more privacy information than the global model. So we did some experiment. Okay, we first of all, okay, we train some attackers. We use some malicious inputs. Okay, we use two techniques. One is label flipping. For example, if this is a car, okay, we can the image on the right, okay, looks very similar to the bees, right? The pattern of the bee. So we can label the cars as bees. Then we can train the malicious model. Okay, then the attacker want to mislead the global model into this malicious model. Okay, with the existing solution, okay, so it's very easy to launch such attacks. But with our techniques, we can. It's very difficult for the attack to do that. The accuracy of this what we call the backdoor model, okay, is very low as compared to the main task of the machine learning models. So this is one example of our research on machine learning security, in particular the privacy aspect of machine learning. So we have some other research going on along this direction, which included like other security issues. And technically, there's a lot of multiple dimensions we can expand from this research, either for physical layer security and for machine learning security. But at the high level, so if you look at the problem, so most of the time, okay, we are staying in our areas. So we use signal processing, we use information and technology to solve the problem. But it's also very important to consider the problem in the whole system level. So which means that we have to integrate other factors such as the physical system properties and also some human behaviors, because the system is not just operated by the devices, it's also supported by people. So therefore, I'm looking forward to collaborations with colleagues and from related and also different disciplines. So this is pretty much my talk. I'm happy to take any questions.
Okay, thanks very much, Shucheng, for a presentation that covers a very comprehensive topic that ranges from hardware as well as software and the related security issues. Now, with respect to the security bootstrapping part of the presentation, right? Is the approach in general immune to environmental noise or interference?
Yes, we conducted, actually we considered the setting we considered is very noisy. So we use the devices we purchased from Amazon, the kind of like just a commodity device. We did experiments in the real world setting. Actually, one is from the Bashar building. Okay, in these offices with people, walking around, and I think this is a very very real setting. So one challenge is how to eliminate this real world noises. So that's one kind of the challenge of the research.
Okay, thanks very much. With that, this concludes the forum today. I thank the audience for participating in this forum, and I also thank our speakers for the enlightening presentations.